Hi there, students. Welcome back to class. This is Mrs. Brunk again, and we are going to be continuing our study of transformations in this next module. And today, specifically, we're going to focus on sequences of transformations. So, some meteorologists claim that the countless number of snowflakes that have fallen since the beginning of time that no two are alike. You may have heard that before, right? No two snowflakes are alike. Whether that's true or not, all snowflakes have a few things in common. I was really surprised to hear this. Every one is hexagonal in its basic shape. I did not know that. And every one displays patterns that show translations, reflections, and rotations as well. In this lesson, we're going to learn how these transformations can be combined to make more complex figures. Then you'll have a chance to chill out, get it, snowflakes, and apply what you've learned to some geometric figures. Recall, a transformation is a function that takes points on the plane and maps them to other points on the plane. Transformations can be applied one after the other in a sequence, where you use the image of the first transformation as the pre-image for the next transformation. So our learning goal is you will be able to draw the image of a shape after a given sequence of transformations. So we're going to basically string together transformations in a sequence, and we will be applying multiple transformations to a given figure. In fact, this is actually a strategy that is used in really all kinds of computer graphics, especially like video games. And that's how they give the appearance of motion in a video game, is a sequence of transformations, one after the other after the other. So like if you wanted to show, say, Super Mario Brother running along, it would be a series of translations that would show that motion. In example 1, we're going to look at one such sequence of transformations. So it asks us to draw the image of the figure in the plane after the given combination of transformations. So let's first take a look at the original figure and the first transformation that we're asked to do. Well, notice they ask you to take the points on the figure in XY form and change them so that they're 3x and y. So in other words, they want us to triple the x coordinates of this figure. So let's first take a look at what the coordinates of this figure are, and we'll kind of map these out right here. We've got one of them, an a, that's at 0, -2. So a is at 0, -2. And then b is at -2, -4. And then finally C is at -4, -4. And if we were to apply this rule of the 3x comma y, our new coordinate, if we called it A prime, now I'm going to do that in a different color. Let's see, so we'll go with like a red. A prime, all that's really going to happen is each of the x coordinates is going to triple in its coordinate. So like if I multiply each of the x's by 3, and I'll just do the x's first, and the y's are going to stay the same. So actually we could write the y's down. They're going to stay the same. This is still going to be -2. This is going to be -4, and this is going to be -4. But I'm going to triple the x's, so 3 times 0 is still 0. -2 times 3 is -6, and 3 times -4 is -12. So let's go over here. We can see if we can graph these. So 0, -2, that one's staying right there, and that's now A prime. It was the same coordinate. -6, -4, so that's left 6 and down 4. So that's right here. So that's our new B prime is. And then our new C prime is -12, -4. So that's right here. And so when we connect that, that figure is very elongated. You can see that basically what happened is it stayed the exact same height, because from like the base B prime C prime to A, it's still the same number of units, same height, still 2 units tall, but then they just made the base 3 times as long, so stretched it horizontally, and that's what's going on here is a horizontal stretch of 3. So the next transformation says to apply this rule. So we're going to take our new coordinates, this new figure, A prime, B prime, C prime, and we're going to apply this rule to get A double prime, B double prime, C double prime. In other words, like the second transformation, so the sequential transformation. So we don't go back to the original figure and use those coordinates. We're doing a successive transformation. You do one transformation, which was the 3x comma y, and now we're going to apply to those coordinates the new transformation, 1/2 x and negative 1/2 y. And so the x coordinates, the first coordinates, are going to be multiplied by 1/2. So if you multiply 0 by 1/2, you get 0. If you multiply negative 6 by 1/2, you get negative 3. And if you multiply negative 12 by 1/2, you're going to get negative 6. Now to get the next coordinates, and actually I'm going to rewrite these down here. And if for the second coordinates, or the y coordinates, instead I multiply by negative 1/2. So negative 2 times negative 1/2 makes positive 1. Negative 4 times negative 1/2 makes positive 2. And negative 4, again, times negative 1/2 makes positive 2. So here are my new coordinates. I'm going to put them on the graph over here in green. So 0, 1, there's A double prime. Then negative 3, 2. Oops, I did it again. I always label them right over top of the figure, because I never quite know exactly where it's going to be. So negative 3, 2. There's B prime. I'm sorry, B double prime. And then finally, oops, negative 6, 2. I did it again. Negative 6, 2. Oh my goodness. So that's where B double prime should be. And then that last one is at negative 6, positive 2. And that's right here. And that is going to be a really strange looking and very difficult to draw figure. So I'm going to connect A to B, B to C, and C back to A. Oops. Let's go. C double prime to B double prime, and then to A. So what happened there is it was actually compressed both vertically and horizontally, and that negative on the Y actually reflected it, so that flipped it over the other way. So the final figure right here, if we compared it to the original, is actually the product of both a horizontal stretch of factor 3 and then these vertical and horizontal compression of 1/2 and that reflection. So really all we're doing is kind of building on what we've been doing, but instead of just doing one transformation to a figure, we are doing multiple transformations in a sequence. So this next one has 4 transformations that they want us to apply. And so I'm going to first look at my coordinates. I'll list them down here. A is at 2, 2. B is at 2, 5. And C is at 3, 2. There's my original coordinates, and then I'm going to apply these transformations. Now the first transformation is, it says to subtract 1 from the x and subtract 1 from the y. So we know that that's actually going to move at 1 left and 1 up, or 1 down, excuse me, 1 left. Oops. So if I just subtract 1 from each one of these, this will give me my new coordinates. So subtract 1 from the x gives me 1, subtract 1 from the y gives me 1, subtract 1 from the x gives me 1, subtract 1 from the y gives me 4, subtract 1 from the x gives me 2, and from the y gives me 1. So here are my new coordinates. This is just going to look just like the original, but just slid 1 unit left and 1 unit down. So each point is going to go left 1, down 1. So A is going to go to this point right, this point right here. And then B is going to go to 1, 4, So over 1 up 4, it's going to go here. And then C prime is going to go 2, 1. It's going to go right here. So again, we're just taking the figure, and it looks just the same this time because we didn't do any stretches or compressions or anything. And I think for mine, because I've got all the coordinates listed here and I'm doing colors, I'm not going to list the vertices on the graph. It just gets so messy and confusing there. So my next one, I'm going to do in blue. And this one says to triple the x's, but leave the y's alone. So my A double prime is going to, in these coordinates, all the coordinates are going to triple the x's and keep the y's the same. So that's a horizontal stretch. It's going to make it horizontally or widthwise 3 times wider. So if I triple all the x's, this would be 3, this would be 3, this would be 6. Keep all the y's the same. And put those coordinates down there. I'll graph that in blue. So 3, 1, over 3 up 1, over 3 up 4, and oops, and then over 6 up 1. So you can see what happened is as soon as I connect this, I guess, you'll be able to see that it was stretched widthwise, but it's the exact same height as it started with. So now see how it's 3 times wider. It's the same height, but it's 3 times wider. Okay. Now the final one says to take the opposite of both the x and the y. So we're going to take our final coordinates. I think I'll do these in, let me see, how about purple? And I'm just going to change these signs, and I'm going to get my final coordinates. So they're going to be A triple prime, B triple prime, and C triple prime. I'm going to run out of room for the next one, but I can always erase. And so these just say take the opposite. So that'll be -3, -1, -3, -4, and -6, -1. And that rule may look familiar to you because this is a transformation we've done. When we take the opposite of both of them, we're going to see what happens to it in just a second. So if I go -3, -1, so go -3 and -1 puts that point right there, and that's the A prime, triple prime. And by the way, the A double prime was at 3, 1. So this was the A. I'm just going to label that one coordinate just so that I can compare it to where it was originally. -3, -4. So that's going to put me right here. And then finally -6, -1. So that puts me right here. And once again, I always label these in the wrong spot. So I'm going to move that. This is A triple prime. Right there. So then connect it and see what I got. I've got, let's see, this figure that you may recognize as a rotation 180 degrees, because if I were to, let's see, find one more color here. How about light purple or dark purple? So if I connect this back to the origin, this coordinate that I labeled A double prime, and then I connect it back to its original image, you can tell that this is the same number of units. So it's like instead of 3 to the right and 1 up, it's 3 to the left and 1 down. And that figure has just been turned 180 degrees on that final transformation. So we've got a slide left 1 and down 1. We have a horizontal stretch to make it triple wide, or when you look at that blue figure. And then we finally took that one and rotated 180 degrees to get to the final position right here. It's our final position. Let's try one more before we move on and look at our next example. So we've got these coordinates, and I'll write them up here because I got space here. So these are our coordinates for the original triangle. And I'm going to do the first transformation in red. So this is going to be my A prime, B prime, and my C prime. And so what it tells me to do is take each x coordinate and multiply it by 3/2, which is 1.5. Well, if I multiply 2 by 3/2, I get 3. If I multiply the 0 of the b by 3/2, I get 0. And if I multiply the 4 by 3/2, I get 6. So now I'm going to do the y's. Well, the y's I'm going to multiply by -2. So each y I'm going to multiply by -2. So that first one would be 1 times -2, which is -2. The next one is 2 times -2, which is -4. And the final one is 3 times -2, which is -6. And I'm going to go ahead and graph that. So 3, -2, over 3 to the right and down 2. This is my A prime. 0, -4, which is right here. And this is my B prime. And then 6, -6. This is the C prime right here. So you can see that this has definitely has changed size, and so there's been a reflection over that x-axis by taking the opposite of the y, and then by doubling the y, we're actually making it twice as tall and making it 3/2 or 1.5 times as wide. So each thing we're doing is changing the figure in some way. And unlike the transformations we looked at for the most part in the last module, these are actually changing the size and the shape of them in most cases. And so they're giving us figures that are not considered to be congruent to each other. So now the final transformation, I'm just going to take these figures, or this new figure, and I'm going to go ahead and subtract 5 from the x's, and I'm going to add 4 to the y's. So subtract 5 from the x's would make this -2, make this -5, and make this 1. And then add 4 to the y's. If I add 4 to the -2, I get 2. If I add 4 to the -4, I get 0. If I add 4 to the -6, I get -2. So here are my final coordinates, which are the double prime ones. So -2, 2, right here. -5, 0, which is here. So that's my B double prime. And then this is A double prime. And then finally 1, -2 over 1 down 2. This puts it in my final position. And when I connect, I can see that this looks just like that red triangle, because I didn't stretch or compress or reflect it or anything, right? But it's just slid. It looks like it's just this exact same triangle, but just slid. Let's see, 5 units to the left and 4 units up. So you can see each point goes 4 units left, 5 units up, and to its final position. So with this particular one, this example, they're not going to give you specifically the rules, but they tell you the description of what the transformation is that's going to occur. So when we start off with our first coordinates, L, M, and N, they'll tell us to slide along this vector -2, 3, which basically means we're going to slide it 2 units to the left and 3 units up, right? So this is 2 left, like that, and then this is 3 up. And then it says reflect across the y-axis and then reflect across the x-axis. So we're going to end up being doing 3 transformations. So let's get that first one down. So we got to get the coordinates. So L is at, let's see, -5 and 1, 2, 3, 4. -5, 4. M is at -4, 2. And N is at -1, 2. And the first thing we're going to do is we're going to subtract 2 from the x's, and we're going to add 3 to the y's. So if we subtract 2 from the x's, and if we add 3 to the y's, here are our new coordinates. Okay, so this is the first transformation, right? And now our new coordinates will look like this. Let's say negative 7 and 7. That's going to put us way up here in the corner. Just barely made it on the page. Negative 6, 5. So negative 6 and there's 5 right there. And then negative 3, 5. So negative 3 and up 5. So we can see that this figure looks just the same as the original. It's just slid, just translated. So, oops, let's draw this a little better. Right here, and 3, 5, which puts me right here. And now I have another triangle that looks identical to the original, but it's just now, it's slid and then reflected. So comparing it to the original, they still look exactly the same. These are called transformations that are either, they sometimes call them isometries or rigid motion. So they're going to keep the figures rigid, not allow them to change, stretch, or compress, or whatever, but just move the position. And one last transformation, this time what they want us to do is do a reflection of the x-axis. So remember that rule says keep x's the same, so I'm going to do that in purple, and keep the x's the same, but make the y's the opposite. So my new coordinates would then keep all the x's oops, I didn't write that right. It's supposed to be negative y, sorry. So the x's all stay the same that they were before in the prior figure, which would be 7 and 6 and 3, but now I'm going to change the y's to the opposite. So it'll be negative 7, negative 5, and negative 5. Here are my final coordinates for my final figure, and it should reflect over the x-axis. So over 7 and down 7, it's going to put us way down here in the opposite corner. 6, negative 5, so that's going to put us right here in that position. And then finally 3, negative 5 is going to put us right here. And now we're going to connect and get our final spot. And the thing that's true about these, all of these triangles, is all of these triangles are identical. Although that one didn't look like it. I didn't connect those very well together. So none of these transformations changed the figure size or shape because we did a slide or translation. We did 2 reflections. And so all of those produce what are called rigid motion figures or isometric figures, figures that don't change size or shape. They are called congruent figures. So in this next question, we're going to take the square HIJK, and the first thing we're going to do is rotate it 90 degrees clockwise about the origin, and then dilate by a factor of 2, which maps x, y onto 2x, 2y. So first of all, what was that rule again that we learned for 90 degrees clockwise? Well, we learned that 90 degrees clockwise was the same as 270 counterclockwise, and this was the rule for that. It was to take the xy coordinates and map them onto y opposite of x. So reverse the coordinates and then change the sign on the second coordinate. So let's first list out these coordinates, h, I, j, and k. So h is at 1, 4. K is at 1, 2. Oops, 1, 2. I is at 3, 4. And J is at 3, 2. So now we're just going to apply this rule to rotate the figure 90 degrees. Now if you think about it, you know, with the 90-degree rotation, the figure should look the same, but it'll be rotated into a different quadrant by 90 degrees. So reverse the coordinates, make the second coordinate the opposite sign once you reverse it. So that would be 4, 1, but then you have to take that second coordinate and make it the opposite, so that'd be negative 1. And then switch these around, that's 4, negative 3. Switch these around, that's 2, negative 3. And switch these around, that's 2, negative 1. So that should rotate our figure 90 degrees about the origin. So real quick, let's plot that. 4, negative 1. This is where H prime is. Then 4, negative 3. which would be I prime. And then j prime is at 2, -3, which is right here. Oop. And 2, -1 is where k prime is. And then all I'm going to do is connect them, and we'll see our square that's been rotated 90 degrees clockwise. Now, as a way of checking it, remember how we can tell is we can connect a point and its image back to the origin. Let's say K back to the origin, and then K prime back to the origin, and you can see that 90 degrees and going this way, right? So we got that 90-degree rotation. So we got the first one. Then they want us to dilate it by a factor of 2, which means they're going to double the x coordinates and double the y's. So all I have to do is just simply double each of these. So 8, -2, 8, -6, 4, -6, 4, -2, and this should just make this double the size. So let's see, 8, -2 is not going to fit on my graph here. That's not good. Let's see, 8, it's going to go off the screen there. So we'll try to do which ones we can. 4, -6, so there's 4, -6, and 4, -2, which is right here. And then the other two go off the page, so we can kind of get an idea though, because it's going this way, like off there a little bit. Didn't do a very good job drawing that. So it would just double the size there. And notice that it's doubling and then it's getting further away from the origin than the original figure is as it doubles. So it's doubling that distance away from the origin as well as making all the lengths of the sides twice as big. So we're going to make this one to be a you try question. So you just want to go ahead and identify GHJ and K, and then you're going to reflect across the y-axis and translate along the vector 5, 4. And so you're going to find G prime, H prime, J prime, K prime, and then you'll find G double prime, H double prime, J double prime, and K double prime. And be sure to graph all three. Well, you've got the first one, so graph the reflected figure over the y-axis, and then the slid figure 5, 4 with the vector 5, 4. And we're actually going to end it there, and we'll follow up, and we'll see how you did when I meet you in class. Thanks for coming to class.